So hello, everybody. Welcome to our last Dashu seminar for 2023. It's been a very interesting year. We have a lot of great things ongoing. We're very glad to the end and hope everybody enjoy your Thanksgiving break and getting ready for Christmas. But we have to keep the spirits ongoing to bringing you guys the data science related seminar. Today we have Dr. Xin Hunt from SAS joining us today, giving a talk. I'm sure you signed up, you already know the general abstract of today's talk. So before I ask Xin to share her content, I will, I'm sharing my, by the way, I am sharing my slide deck. I will make a few announcements and also introduce us to the new members who just joined Dashu as the audience today. So we are a 501c nonprofit organization founded 8 years ago. We're dedicated to promoting data science, relevant seminars, workshops, online and offline scientific conferences to you all. And we also are actively engaged in professional engagement, and popular topics is ongoing. If you guys sign up 5 years ago, you will notice today's topic is drastically different from 5 years ago. There's a lot of advancement of the AI in the industry and in the world happening. We are a big, lovely family. If you're interested in joining our volunteering work, feel free to reach out to us. You have all of the means to, shoot us a message, like emailing us or check our social media channels. This is our happy family. Everybody's doing their own volunteering work. Again, we need your help to run our entire organizations. So next year, we're hoping to do another round of on-site scientific conferences like we did one before the COVID. So in order to do that, in order to allow us to bring you the best in class data science related topics and discussions, we need your support. And thank you all this year who registered our seminars, and thank you for your donations. We eventually reached our goal. But like I mentioned, we cannot survive without your generosity. That is why I would love to, express how grateful we are to Beijing for, folks who joined last seminar and also for, today's seminar. You may know that Beijing is our proud sponsor for our 3 scientific data science seminars. And I would love to introduce Beijing values today. I don't know if Jinjing is online, and many thanks to you and to your team. So I'm sure you all know Beijing as a global commercial stage biotech company that is dedicated on discovering, developing, manufacturing, and commercializing innovative medicines to eventually improve patient treatment outcomes worldwide. Here I'm listing their Beijing core values are patient first, bold ingenuity, driving excellence, and collaborative spirit. And I'm also very honored to introduce their Beijing One app, B1 app. So you can see that Beijing is committed to eventually reducing the burden of cost of drug development, and they hold this for excellence, portfolio excellence, operational excellence, technology excellence, and data excellence. And this excellence is actually the foundation of their data science team and digital innovation department within their global statistic and data science, and they're leading the cross-functional team to develop this B1 app. This is like a super app that I myself am also experimenting out. It is built upon clinical enterprise data acquisition repositories, and it was able to empower and accelerate business functional teams to derive real-time data insights and make data-driven decisions. These are all the core values that Dashu as an NGO also holds truly. So thank you, Beijing, for your generosity and help and support. I've always advocated, hey, if you're interested in nonprofit and volunteering work, join us. But also as a health professional dedicated in data science industry, I do believe Beijing is also a great place to be part from a team for to eventually making a difference for the patient lives. So thank you. And also if you're interested, check out their career website to join their wonderful team. So I also encourage everybody to stay tuned for our opening Dashu seminar next year in January. We haven't really knocked down to a specific date. So that's why I have to subscribe to our email blasting service to not miss this wonderful topic and seminar and opportunity to meet Dr. Lu. Dr. Le Lu is actually our previous speaker from about 2 years ago, and he joined the Damo Academy, and he leads in Alibaba Group, and he leads the global medical AI and R&D initiatives. He I remember last year, about 2 years ago, he was talking about their deep learning imaging work related to the pancreatic cancer diagnosis. And it's remarkable for us to witness Dr. Liu's work in only 2 years has been translated and making huge clinical and diagnostic impact to tens of thousands of patients in multiple hospitals in the East Asia, Great China region. So their team just published a Nature Medicine paper this month, and we're very glad to have Dr. Liu coming back to us next month to give us this wonderful talk. So check out this seminar, and also thank you again, Beijing, for sponsoring that seminar next year. All right, without further ado, I would love to get to our today's speaker and topic, Dr. Xin Hunt. She will give us a talk about explainable AI, model-agnostic interpretability in machine learning, which is actually the area that she has been a rising star and now is a world-leading scientist in the machine learning interpretability research work. She is currently a principal machine learning developer at SAS, and with the focuses on machine learning, model interpretability, the AI fairness. She received her PhD from Duke University in electrical computer engineering, and I'm sure she's going to touch base on many useful case studies about that machine learning interpretability topic. So Xin, I think you're a co-host. I'm going to stop sharing now, and welcome to Dashu and giving our talk today. I look forward to it. So feel free to share your screen any minute. And by the way, you're on mute.
All right, thank you so much for the introduction. I was just trying to figure out, we use Teams mostly in the company, and I was just trying to play with Zoom to trying to make sure I'm sharing the right thing. So that took me a second. Hopefully you can all see the screen now.
Yep, perfect.
Okay.
Thank you.
All right, great. So again, my name is Xin Hunt. Thank you all for joining this meeting today. I am going to share today some interesting methods in model interpretability. So let's see. Okay. So the agenda for today is we're going to first talk about what interpretability is in terms of machine learning. And we're going to talk about several dimensions of the interpretability, how you can categorize it. It's like when you talk about interpretability, what we really are talking about. Then I'm going to show you several very common methods. So today's methods, we're going to focus on the model agnostic, local, and global methods. We're going to talk about the definitions of these if you're not super familiar with them, but these know that they are basically, if you're using general machine learning models, these are the most popular methods, and we're going to discuss how they work and what you can get out of them. Machine learning interpretability is very much a work in progress. It's not a super mature field. There are new papers coming out every year. So there will be new stuff all the time, but these are the current cutting edge, most popular. So we're going to talk about them, and then we're going to look at some examples, how you can use them and interpret the results of models. So what is interpretability? So interpretability can cover a lot of things. When we talk about machine learning model interpretability, what we are mostly talking about is the ability for us humans to understand a model's behavior. This is important for a lot of reasons, and they are very model and context dependent. So it depends on what your problem is, what kind of model you choose, and where your end goal is. But in general, it can answer questions. For example, why are some loan applications rejected? Why is the prediction going up or down? And even some like fairness related questions like, did this model use a feature or variable that I do not want it to use that is currently protected? The reason people started looking at interpretability was because as machine learning progressed, we're starting to use bigger and bigger, more complex models, neural network being one of the most easy examples. That's why I showed them here. This data is actually a little bit old now. As you see, the years listed on this table is up to 2015. But even until up to that point, the parameters are in the number of millions. Now, the big models are even bigger. And I'm not saying that we have solved this problem, that we can explain everything with those super huge models, but I'm saying that people are working on trying to understand these. As you can imagine, trying to look at the parameters and understanding what the models are doing is near impossible just by having the model itself. That's why researchers and us people who develop software are working very hard to try to give people using these models a chance to understand what they are actually doing. And here I list a few reasons why we need interpretability. You can imagine uh, whether you're selling a model or you're building a model, it's important that you understand what it's doing, especially if you're working on a highly sensitive or regulated field in medical, finance, insurance. You have to make sure the model is worth your trust, right? If only because the model gives you good predictive power over your training set doesn't all mean it will give you good predictive power in all the future data sets, and it doesn't tell you if the model is truly fair. There could be repercussions if you're not careful about that. Also, the robustness I list here is interpretability methods not only can help you avoid some legal issues, but also it can help you debug. If it tells you what the model is doing, if you see some weird behavior in models, you can try to interpret the model and see behind the scenes what possibly could have gone wrong. This is similar to the learning I listed here. If you understand the model, why it's making certain predictions, it gives you a better chance to make better models in the future. And of course, the legal requirements for example, credit, insurance companies, they're required to give reasons for why they reject an application. And so they have no choice but to choose a model that can be explained. Here, and a lot of people might, or you might ask, like, why can't we just keep ourselves to some simple models that are easily interpretable? My answer is this: yes, you can, but for a lot of applications, you either would like a more accurate, more complex model. For example, if you delve into anywhere into image recognition, it's impossible really to just use linear regressions or decision trees. But also, even in the field where these might be sufficient, there are still questions that cannot be answered by just using these simple models. I'll give some examples. For example, we think linear regression being one of the easiest models to interpret, where you can just write out the formula and say, okay, the coefficient tells me how much my predictor increases by one, right? As x value of x increases by one, what does the expected value of y increases is my coefficient. So that gives you a very clear idea of what the model is doing. However, if you have complex feature engineering, you have feature interactions, and a lot of the times the features that end up in your model are not easily understandable. And in many cases, you would like to explain it in the original feature space. So that would place some complexity in terms of interpretability. Trees is another example. A small decision tree and rule list are pretty interpretable. You can look into each split of the tree node and say, okay, so in the first node, we're looking at variable x. If x is bigger than a certain value, we go to the left branch. If it's not, then we go to the right. And you can understand what exactly the model is doing by looking at the model itself. However, even this, sometimes there are questions you cannot easily answer. For example, this is a relatively simple, small decision tree trained on one of my favorite easy data sets. It's called Iris. In case you're not super familiar, it has 4 numeric variables, the petals length and width, the sepal length and width, to predict the species of this iris flower. And there are a total of just 150 observations. You can train a pretty good model on it pretty easily. And yes, I can look at this tree and tell exactly at each step what my tree is trying to compare. Okay, the first one is look at the petal length. If it's shorter than the amount I have a prediction. If it's larger, then I go somewhere else and have other splits and find out more information about this observation. But just looking at the tree, even this is not clear to me. How do you quantify what is the most important variable, and what about the third most important variable? How do you quantify it? And is that the same for every data point and prediction? You can say, okay, maybe the most important is the petal length because that's my first split. Yes, but for data points that fall onto the right-hand side of the tree, what about them? What are the most important separating decisions for them? So the things go on, and if you have a tree that's any much larger than this, for example, you have a 15 depth tree or even larger, you allow, for example, multiple branches, not just binary, then it quickly become intractable. And we're not even talking about forest or gradient boosting where you could have hundreds or thousands of trees. And because even understanding one tree could be problematic, right? Not that simple as you would think. And it will be eventually, when you move on to more complex models, you need some other methods to tell you how to do this. So to recap that, a lot of the considered open box models, again, they're great if they fit your need. I'm definitely not saying don't use them or anything like that. If they fit your need, they are still very clear, very open models that you can understand them much better than any other models. So if they fit your need, definitely try them. They are reliable and well-defined, but just having open box models does not answer all the interpretability questions, and having high dimensionality in your data, having increased complexity, ensemble, pre and post processing, like feature engineering, can add all these complexity to interpretations. So hopefully I have convinced you by now that there is a need for interpretability methods. And what is interpretability? Again, now we've gone through all these things. Let's revisit this. So what we want is not necessarily understanding all the details and logic about the data for every data point, although it might be nice to be able to, but there are some like pressing questions, common questions we would ask. What are the most important features for a model or a decision? What happens if some of the features change values? And are there features the model does not use, or is this the feature the model uses? And is there a difference in the decision-making process between groups? The last question is especially important if you're caring about like fairness among different ethnicity groups or among different populations. So that's one of the questions that interpretability could help you with. A few use cases, just we're going to go through this pretty quickly because I don't want, there are a lot of things I want to cover today. For example, you could have financial institutes that needs to give reasons for denying credit. And here is an example where you would want to know, okay, what are the most impactful features, not only on my overall model, but on each individual decisions. And also, like fairness, I just talked about. For example, if you have student admissions, you may want to know, okay, does my model give a fair prediction for each student group? like for example, counties or of different locations. And you may also want to ask, okay, retroactively looking at the data and models prediction already made, did my model make fair predictions for different groups, right? Another use case is like, for example, I have a model predicting system failure in the future. And if you don't know how the model is making the decision, then it's going to be hard to troubleshoot. If it can tell you what feature likely contributed to that prediction, then you could investigate the reason more easily. And also crop selection, which it could help you figure out what features are most impactful on the trial succeed. And there are also examples, for example, in medical or biology field, protein engineering. If you could explain a model that predicts the heat resistance, then you can figure out what combinations of amino acids or structures could contribute to your desired characteristic. These are all examples, and we're going to talk about the dimensions of interpretability next. Basically, there are some jargon words about interpretability like pre, during, and post-modeling. What does that mean? Pre-model explainability easily is before you build a model. Those usually involve looking at the data, visualize the data, analyze if data is balanced, if you have a group that's very small, that's difficult to predict. And you can also try to choose and construct interpretable features from the data you have. During modeling is basically use more open box models. For example, the ones we talked about, regression, ruleless, tree-based models, and add constraints like monotonicity and fairness constraints while you build the model that ensures that the end result in your model does not violate certain things that you would like to have. And post-modeling is the ones we're going to talk about today, is interpret existing models and decisions. The model, you already made it, and we're going to analyze how it behaves and why it behaves that way. So a lot of these common methods, you can do sensitivity analysis, feature importance calculation, and you can build surrogate models to understand the local behaviors or construct model-specific explanations. And we have also, you can also classify the interpretability methods based on model-specific and model-agnostic. So this is fairly simple. Model-specific methods simply means that it's built to explain just one kind of models. It uses model-specific information, so it usually gains a lot of insight because it knows how the model is built. There are many deep neural network specific methods, which we're not talking about today, but if you're interested, there are seminars and the papers out there you can look at. And model agnostic methods are the ones we're focusing today. Is they work with most machine learning methods. It basically treats your model as a closed box. So it doesn't know the inner workings of the model, whether it's trees or regressions, or it has a deep neural network. What it usually relies on then is input-output analysis. So most of these methods will look at your original training data, construct a lot of new inputs, feed it into your model, and see how the model behaves based on the input and output, analyze or take a guess at how your model is behaving. There is also you can also classify the methods into global and local. This is not like super clear, but mostly global explanations tells you overall behaviors of the model. For example, the global feature importance overall, which feature is most important for this model, or partial dependence, we're going to talk about it later. Local explanations tend to focus on either one specific prediction or a small specific region of your data. Usually it explains a particular decision. For example, you can ask, for this specific observation, I made a prediction, what is the most influential variable for this decision? And that is often different from the global feature importance. And we're going to talk about Lyme, ICE, individual conditional expectation, and also Shapley values in this in this talk. So before we start going into the methods, so all of the examples later I show for the specific methods are based on this synthetic data. This data, well, we use synthetic data because it makes pretty plots and it's clean and easy to understand and shows you the effect most easily. Of course, in real life, we don't have synthetic data, but I feel like if the methods show something in the synthetic data, at least it gives you some confidence that, okay, if it works here, it might also work on the real data. And this data particularly has 4 inputs, all of them numeric. It has a linear effect of x1, sinusoidal effect of x2, parabolic effect of x3, and absolute value effect of x4. We also added some noise to it, so the observations are relatively noisy. It's not super easy to look and see to predict if you don't know the underlying model. But for this specific one, I used GAM, and GAM made pretty good predictions on all of them. And specifically, we don't allow spline on X1 because I already know it's linear and it makes pretty plots. So that's cheating a tiny bit, but the results are, like you see, the predictions are pretty good. And we're going to first talk about the individual conditional expectation. And with that, we'll build us up to partial dependence. So what individual conditional expectation does is evaluates the effect on the model's prediction by changing the variable's input value. So it is a local method. It focuses on one specific observation and one specific variable. So basically it answers the question of, if I pick a variable and change the one variable up and down, what will my prediction be? So that, for example, what happens to my credit score if my history is longer? What if all of these what if questions can be answered by ICE? The steps are simple. You pick a specific variable and you pick a specific observation. You replicate that observation, substitute a range of values for the variable you're interested in. You score all those new observations with your existing model and plot out the predictions. You can repeat that for other observations. You get multiple ICE plots. So here's an example. We picked one, I don't know if you can see my pointer. Okay, right here. So we pick out one here and, okay, how do I get rid of? And then you change the value of the variable that you picked. The x3 is the variable I picked, and you change the values and score these new observations, and you can plot out these predictions. You can repeat it for different observations, and you have a series of ICE plots. So here it shows pretty clearly that how x3, remember, it's the parabolic effect. So here ICE explained that effect around this variable pretty well. And partial dependence is on the other hand, a global interpretability method. Instead of evaluating one variable on one observation, it explains the effect of one variable on all of the observations. Basically, it's more about the trend of a model. How does the model's average prediction change for different credit history lengths overall for everybody? What it does is simply average all of the ICE curves for every observation. You can also consider variable interactions by calculating multi-way PD. And however, partial dependence, here's one thing I listed here. Partial dependence does not consider feature correlation. If your feature is correlated, you should it considers interaction in the model, but not correlation in your data. So if your data is correlated and you're concerned about that, you could consider using accumulated local effects, which considers data dependence on the other hand. So remember, we did all these ice curves. If you plot these for all of the observations and then you average them all, you're going to get what is on the right-hand side, which is just the average of all the ice plots, which is the partial dependence for X3. That's relatively straightforward, and I plotted out the partial dependence for all 4 variables. As you can see, for GAM model, X1 is very straight, and X2 shows the sinusoidal effect, X3 the parabolic quadratic, and the X4 is a smoothed up absolute value effect. Next, we move on to LIME. LIME is a very popular method. Its name came from the locally interpretable model-agnostic explanations. What it is it evaluates the coefficients of a linear model trained on the predictions around some individual observation. I'll explain that a little bit more. I know it's very wordy and you might not get all of it from just one pass. But what it does, really, a lot of people think of LIME as feature importance, but it's not really feature importance. What it tells you is the trend of the model near that one specific observation. So LIME is a local method. LIME explains single observations. So the first step you do it is to pick a single observation. And what you do is perturb your data to generate random observations somewhat close to this observation you picked. And then you score using the model with all those randomly generated observations, and you weigh the observations based on their proximity to the one you care about, that you want to explain. And then you train a linear model on all these data and their predictions, and you look at the coefficients and explain it. So what this does is it trains a model that's based on data close to the one you picked, and it weighs everything towards the data you pick. So the closer it is to your point of interest, the higher weight it receives for this linear regression. So in the end, it gives you a local trend for your model at that point of interest. I think it's a little bit easier to see if we show an example. So this is the partial dependence we saw earlier. And if you just select one observation, I selected one, and here is the point shows its location for each of the variable. And now we generate some local samples that's close to it based on the definition of local we used based on the distribution of the data in that variable. And then you do a linear regression on all those data and the model's prediction. And the coefficients are the slopes of all of these red lines. And you can see what it does is really fitting a tangent line to your local location at the point of interest. It's not exactly at the point of interest because all the other all the other randomly generated observations, although you're weighing it towards the point of interest, it not necessarily falls exactly on there. But it basically tells you, okay, for example, X3 at my point of interest, the slope of the local model is roughly going down. And the X2 for this variable at my local area, the model is going up. So what the coefficients really tells you is the trend. To summarize, LIME fits a local linear surrogate model to data generated around the point of interest. There are some issues about LIME. For example, defining what's local, you need a definition of that. There could be multiple definitions, but you have to choose one that works for you. And of course, since we're weighing the data towards the sample, how heavily do you weigh it is a question. And also, when doing linear regression specific for Lyme, we use lasso. So how many features do you select with it is also a question. It's basically how much do you penalize them. But in summary, if you solve all of those or just select something that makes sense, not necessarily super accurate, but it will tell you a local model trend. It is not necessarily the local feature importance, but it tells you, answers questions like, okay, if I want to change my prediction, what is the feature I should choose to move? So for feature importance, Shapley values are a better fit. I'm going to talk about Shapley values next, and that tends to be a lot of people want to know is, especially for example, the credit for credit prediction, like if you're denying a loan, you have to tell them which feature was used to deny their loan. That is really a Shapley value question, is which of the feature gave you the most negative effect. But Lyme will tell you if you want to improve your credit score, which feature to change gives you the fastest change because it's a slope. And common, Shapley values has its history started from 1953, where they were solving a problem of game theory by Shapley. The question was, how do you solve the problem of reward distribution among multiple team members? Imagine this scenario. You have three people, A, B, and C. They earned together a reward of $15,000. And what is the fairest way to split the money among them? Assume we know that if you have nobody in the team, you're earning 0, and having one person earns 4,000, having two people earns slightly different values, and having three people earns you $15,000. Well, you could think that, okay, since each one has makes 4K maybe just equally, but having them a different team composition is going to give you different earnings as shown in these three rows. So clearly A, B, and C still give slightly different contributions. And it turns out if you just set a few easy, pretty reasonable constraints, you're going to have just one solution. The constraints here, I'll talk about them quickly. Efficiency. So basically, everybody's rewards should add up to the total earning. Dummy, if adding someone does not give you any additional value, their reward should be 0. Say there's a person D, adding them anywhere does not change your reward, then you would say, okay, this person doesn't add any value to the team, then we're not going to give them any reward. Symmetry, if two individuals add the same value in every possible scenario, of course, they should receive the same reward. Additivity, if including one person adds the same amount of two, so you can basically add them together, Y and Z, then X should receive the sum of Y and Z. Yes. So if, say, a person would increase the earning by twice as much as the other person, then this person should receive twice the reward. So with all these pretty reasonable assumptions, constraints, there turns out to be only one unique solution. And what you have to do, very simple, is to calculate a weighted average of all the additional value the individual brings by including that person in all possible scenarios. It sounds simple, but what it will entail is if you want to calculate the contribution of A, for example, you would have to look at, okay, having A versus not having A in all possible combinations. That means nobody, having one person, which is B and C, having, well, in this case, and having B and C together. So it's not just a one simple look, and you look at all these scenarios and you construct a weighted average. No, there's not a simple average. There are some weights based on the number of combinations you have in each scenario, and you weight it out, and you can calculate the final answer to how much each takes. The quick answer to give you an answer to this, how to best attribute is A would receive 4.5 thousand, B receives 5,000, and C receives 5.5 thousand, and that adds up to 15,000 as the whole team. So later on, in recent years, not we, but the researchers extended this to feature importance in machine learning models by evaluating the model's predictions with different combinations of feature values. It's imagine including one feature or not including one feature in the model prediction in all possible scenarios would give you an estimate of the importance of that feature in that model. Of course, you don't want to retrain your model 100 million times, especially if you have a lot of features. That's going to be very expensive. But because you're looking at the combinatorial number of possible scenarios, Shapley values, unfortunately, is very expensive to compute exactly. So luckily, we have several approximation methods available. The most well-known being the SHAP, SHAP, that's open source. It's also existing in SAS. SAS has its our own patented methods called HyperShap, and there's TreeShap as well. So those are all approximation methods that aims to increase the speed by approximating the Shapley values without having to calculate every combination of the features. So this Shapley values answers important questions like, what feature contributed most to my current credit score and how much did it contribute? This is like, say, okay, each team member is one of my feature or variable. A, B, C are my three features. Which one of them contributed the most to the prediction of 15K? And here is just I'm trying to show you is for linear models where there is no feature interaction, the Shapley values are simply the partial dependence values at the value of the variable. So if I plot out the Shapley values of this observation that I chose, the feature, the Shapley value for this one will intersect the partial dependence plot at the point of X. Exactly. So that's what Shapley value is for linear models. So that tells you it's really additive. But for with feature interactions, this does not hold true. Even if there was no interaction in your data, if the model, for example, if you use a forest or grid boost where the model tends to add in feature interactions, this will not hold true. Okay, I'm not sure, are we supposed to just take questions at the end or do we take questions between sections too?
I think, folks, if you have questions, feel free to leave them under the chat and Dasheen, maybe you can go on. We usually address them at the end of the talk.
Okay. All right. So let me, the next I'm going to show two case studies, which is in the Python notebook. So I'm going to stop sharing this one and start exit my share the screen, something else. Okay, hopefully you can see this already. So this notebook, I have two examples. The first is going to be a brain tumor detection. No, sorry, this is lung sorry, it's not brain. It's a I think a lung tissue scan. And what this is the lesion detection in the CT images. And so what we did was the computer vision team in SAS a few years back, they built a model to identify the lesions in the CT images. They trained on some ground truth labeled by clinical experts. And then the model would give out these boxes, and the numbers represent the probability the model thinks that could be a lesion. So one question they had was what threshold to change to try to set to display all of this, because if you set the threshold too high, too low, there are all problems. If you set it to a high threshold, for example, on the left, what you end up with is only several lesions per image, and it doesn't include all the lesions that are actually there. The middle image is the ground truths labeled by clinicians, and you can see there are actually 5 boxes in this case, but on the left, a high threshold would only return 2. But if you turn the threshold lower, you would have false positives, where you have lesions labeled which are not really lesions. So that would create problems too. So what we wanted to do for interpretability was to look at those marginal cases where the probability of detection is low, but is not low enough to be dismissed. The high confidence detections where the probability is, say, higher than 60%, usually they're pretty easy to see well-shaped lesions in the images. But for the marginal cases, sometimes it's very hard to see if there's actually a lesion. What you would do instead is, so what we want to do is give those marginal cases to the clinicians. They would have to hand label them and help identify in the images. So for example, here is a image with high probability lesion detections. The 2 of them has pretty well-defined lesions in them, and the marginal case has just a little bit of a shadow in the box, but it's not super, the computer, the model isn't super confident whether that's a lesion or not. However, if you zoom into that box, it's actually a little bit hard to see what that lesion could be. So what we did to interpret this is to run this model through our Shapley explainer. Basically, this boxed prediction, we treat it as one prediction, and then we ask Shapley values, okay, which pixel in this image contributed positively to the prediction of it being a lesion. So basically asking the question, which pixel made the model think it could be a lesion? And what Shapley value did was labeling all the positively contributing pixels in red and negatively contributing pixels in green. So basically saying, okay, these red pixels is what made the model think this could be a lesion. The green, the model thinks probably not so much, but so you could look at this picture based on color coding and see if you see anything in the red area that could potentially be a lesion. So we built this system hoping to help clinicians. If they have a marginal case, they could look at the explanations and help them identify if there's an actual lesion or not. Another example I wanted to show is a school admission model. This I've talked very, very briefly in the slides in the earlier before we talked about the methods. Basically, this is built on a data set. The data set is not real, it's generated, but just to show the effects of how you could use the partial dependence to and ice plots to help you with fairness. So basically, we have a data set where we have SAT score, highest math level class learned that the student took in high school, the GPA, and a normalized score of extracurriculum activities, and the high school ranking in the county. So those features that we would train a model based on these features to predict its acceptance in one of the colleges. And this is the plot is the average effect and admission probability based on the features. So it's basically the PD plot. So this uses the our partial dependence action in SAS, and you can see that the SAT score, highest math, these are the two most influential features that if you increase them, you significantly increase your chance of acceptance at the school. The GPA and extracurriculum activities make a difference in the model, but the high school ranking basically is not being used by the model at all, because even if you vary the variable, there's no change in prediction of the acceptance. And then what we did was also plotted out the ICE plots by county. This is a selected subsample of the students. This is not all the students, but for each county, we selected a random 10 or 15 students, and we plotted out their ICE curve based on the SAT score, because it's one of the most influential features. And you could see that there is a discrepancy between the two counties. And we would like to investigate, like, why would the same SAT score for these two counties end up having different probability of admission? So what we did was go back to the data, plotted out the normalized mean difference between the counties on all of these features that actually that are actually used by the model. And what we found out is SAT score, GPA, and extracurriculum scores are roughly the same between the two counties, but the highest math level class, the county A has significantly higher average math class numbers than county B. If you plot out the density of the student distribution in this highest math class level, you can also see like county A students tend to have a lot higher math class levels, while county B students don't. But then you have to ask, is it fair to allow the model to make this use the feature between the two counties the same way, when clearly county A students had more chance of taking higher level classes? Basically, there's almost no students in county B that had classes over level 6. It's just not offered in the county, then it may be unfair to use it. So what we did instead is to rebalance the data, went back to the data, rebalanced it of this based on this feature, and trained a new model on the rebalanced data. And the rebalanced data got basically rescaled the highest math class for county B and A. And in the end, if you train a new model, now you see that if you have similar SAT scores, whether you're from county A or county B on the right, you will have similar chances of being admitted to the school by this model. So this just wanted to show you, you could use partial dependence and ICE plots to look at the discrepancies of the model on your subpopulations, if that is of interest to you. All right, that is my presentation. Let's see, do we have any questions?
Yes, we do, Sheen. Thank you for the presentation. It's very informative. We have some questions posted in the chat. I also have a few questions. So starting with Eugene. Eugene asked, could you recommend a book or course that looks into this topic at the same level of detailization and examples?
That's a very great question. Thank you, Eugene. Yes, I do have I don't have a course recommendation, but I do have a online ebook recommendation. Let me think about just quickly. There's always one that we liked very much. Let's see, Christopher Molnar, I believe. This book looks a little bit different from what I used to. I think they updated it recently, but I think this is the book. Should I just copy it here? Interpretable ML book. If you just scan the index or the list of the information, you will see it covers a lot of the methods that I talked about today. And there's ice, lime, Shapley values in there in local model agnostic methods. I think this is a pretty good open to everyone free resource that can be used. And I think he explains everything very well.
And thank you, Shin. I also have a similar question following the CT scan, as one of the audience, Yun Zhao, asked. I do believe that is an axial abdominal CT scan of liver lesions. It was
Mm-hmm.
not important. I think the question is more about, is there a Shapley package slash algorithm specifically designed for images segmentation models, and how long is it going to take to explain one photo?
Oh, thank you very much for the correction. See, this this example was
That's
given
fine.
to me I did the coding a few years ago. Now I already forgot what it was, but yes, you say it's a liver scan. Yes, that reminds me it is. Um, yeah, I'm not a medical expert, so these things are not super clear to me just upon looking at it. To answer the question though, I do not believe there is currently a Shapley package or algorithm specifically designed for images. Actually, in order to um, do this, we did I used SAS for the specific method, but the SAS packages are built for tabular data. So it's not directly meant to be used for images. Actually, to do that, I had to convert the images into just pixel by pixel tabular form to use Shapley in that case. I think the open source SHAP package is also designed for tabular data. So unfortunately, I don't think that's available yet. There are, however, other methods designed for deep neural network explanations, which actually I did not include them because that's not the focus of my topic, but they may actually be more suitable for image applications, and you will have to look into that. How long does it explain one photo? In this specific case, because it's not super, model agnostic methods, especially Shapley values, tend to be slow. In this specific case, I believe it took around I want to say 15 to 30 seconds per picture. So because the number of features is so big, we actually had to reduce the feature space a little bit too. But yes, if you're working specifically with images, I would recommend looking into one of those that are designed for deep neural networks, because I'm assuming like image processing, you're using some kind of neural networks. If you're using some kind of traditional trees and a grad boost for your images, that would be an entirely different story. But at that point, you probably already have tabular data, and tabular data can be fed into regular Shapley methods.
Understood. I know we're at time. I just have one last question for you, Shin. Thank you for the talk. So while we're on that topic of tabular data image, Could you just briefly comment on what are the overall challenges for model agnostic explanations for these image data, tabular data, the trade-off between flexibility, interpretability? Because I myself and I'm a computational biologist, we work with high-dimensional genomics and also medical imaging and histology kind of stuff. So I don't know, when data is like structured, not so sparse, what are the challenges we're facing? Um,
So model agnostic methods tend to, their main challenge, I would say, is because you don't know anything about the model, how it works. There's limited things you can do, right? All your model explanation is based on input and output. So you have to change your input, and basically what you're, it's like looking at it's almost like looking at a person, just look at what they do to interpret their inner workings and see their motives. Is it 100% accurate? It's like, can you say with 100% accurate confidence that that is how the model behaves and will behave forever? There's Because you only have access to input and outputs,
mhm.
there is always a chance for making a mistake. Like
I
there are
see.
cases you didn't test, there are areas you didn't explore, so there could be exceptions to the general rule you made. But it is looking at the general behavior of the model. So a lot of the times, if your input output falls into the range that is tested, is reliable. If the model does this, it will do this. But yes, because you don't have access to the inner workings of the model, it's it could make mistakes, and also it takes the complexity could be high because you have to run the model over a lot of data. Um, Model specific methods, of course, the challenge is you can only apply it to one specific class of models, and what it explains depends on what you know about the model. And if you change your model, you say, okay, I want to run a pipeline where I compare 20 different models, different types of models, not just 20 different models of the same class, and see which one performs the best. Then based on the methods available to each model, you could, okay, this specific model, you have a method to explain the global feature importance. For that one, you cannot explain the global feature importance. You only have specific observation importance. For the other one, you have this. For that one, you have that. So it will depend a lot on what is available for each model, and you can, sometimes it's hard to compare them. Model agnostic ones, on the other hand, you can run the same method for all of them, and then you can see, oh, okay, for model one, this is this, for model two, this is that. So there's, of course, a pros and cons in having specific and agnostic methods.
Got it.
Does that answer your question?
Yes, 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 yes. It's a pretty well answered open question. Thank you, Shin. So I think we're over time, and I really appreciate for coming here, and thank you for all of the audience who stayed through the seminar. And please stay tuned for our next upcoming seminars. And thank you again for coming, Shin. And I hope you had a good Christmas and Happy New Year in advance.